Hello, everybody. My name is Taejin Oh. Can you hear me? I'll be talking about the dynamic core development efforts that's being done in KIAPS. This is my outline, so I'll be introducing what KIAPS is. It's a new organization, and the dynamic core design considerations, and some results on 1D CGDG advection and shallow water equation results, and 2D global shallow water equation results, and then the conclusions. First of all, I'd like to thank Professor Frank Giraldo for accepting us in NPS for 3 months and teaching us CG and DG methods, and also Dr. Michael Kopra and Shiva Gopala Krishnan and Lester Carr for having lots of fruitful discussions. KIAPS is a relatively new organization. It's formed. It's a 9-year project. It stands for Korea Institute of Atmospheric Prediction Systems. It's a 9-year project, and starting 2011 until 2019, it's being funded by South Korean government for a total funding of approximately $100 million USD. Dr. Youngjun Kim, formerly from NRL, was appointed as director since last March. He's right there, over there. And our vision and goal is to develop our next generation operational NWP model for Korea. So we have a 9-year roadmap. We're right now in stage 1 to establish the foundation and development of source technology. In stage 2, developing the test model, and hopefully by the end of stage 2, we'll have a version 0.9 global model for KIAPS. And then for stage 3, which will be an operational testing stage, where we'll be tuning and doing lots of semi-operational runnings. So let me talk about the dynamical core design considerations. So the new move about developing new dynamical cores is mostly, I think, is because of the supercomputing trend. As you can see from this graph here, from the top500.org, you can see that the performance is usually increasing 1,000-fold every 10 years. And in the past, that's been done because the CPU clock speed has been increasing, so no work had to be done on the model code. So we were having free lunches. But after then, we are now reaching a problem where the heat is becoming a big problem. So instead of increasing the clock speed, now the cores are increasing. That means that the parallelism has to be well implemented in the code. And so scalability will be a big issue as we go on and on. Right now, KIAP and the KMA has a system that has 45,000 cores. And if we say that we're following this trend, by the end of the project, we are expecting to have a computer system that has the computer power of all 500 supercomputers that are available right now. So that's a huge computer resource, and we should be able to exploit all that cores. That means scalability will be a big issue. Right now, currently in Korea, we're using UKMO's UN model, and this is a result published by the MOSAC report in 2011 by Brown and Wood. As we can see, with various configurations with input or output, or I/O, most of the model is being flattening out, and the parallel performance is now saturated near 1,500 cores. So this is the current state of our in terms of scalability in real operational models. So for us, we had some requirements that had to be fulfilled, and mostly that would be the case for every other organizations. We're aiming for a global non-hydrostatic model, which is highly scalable without pole singularity on the grid structure. That means we're getting rid of the long grid. And we want the numerical procedures to be local as possible to minimize the communication. Mass conservation, higher accuracy, yet computationally efficient. That means that satisfy the operational cutoff time. And optionally, we would like to have AMR capability as well. So according to these requirements, it seems like we're going to ditch the long grid, and we won't be using the global spectral method. So according to those considerations, we came up with 3 options. The first option that we considered was having a icosahedral or spherical centroidal Voronoi tessellation type grid with finite volume. Noticeably, there are many models that are pursuing this path. MPAS, NIM, FIM, ICON, or NICAM are pursuing this path. Option number 2 is having a cubic sphere grid with spectral element or DG type numerics. KIAPS and MPS NUMA are taking this path. And option number 3 is taking a yin-yang grid, which is, we considered this because it's relatively the most easiest path to implement. And it's a finite volume grid, and right now, to our understanding, CMC GEM is pursuing this path. However, after lots of debates, we think we will pursue option number 2, and the reason is because scalability. The models that incorporate spectral elements or DG show unparalleled scalability results. This is the result for KIAPS published in 2012, Dennis et al. With full physics. As you can see, it's scaling with 100,000 cores. This is the scalability result for NUMA, CG, and DG. The blue line is the DZ results. This is the wall clock time, and this is the speed up. And the red line is the CG results. CG means spectral element. So this is a case for rising thermal bubble problems, and we can see that for DG, it's almost like perfectly scalable. So why does CG and DG show this kind of scalability properties? Is because the communications are very small. For CG, the only communication occurs for this particular cell, the surrounding cells. We communicate with those 4. And for DG, this communication is even smaller. So we just need to exchange flux information that's sharing edges. If we compare this to FV, finite volumes or finite differences, the computational stencil that you have to use for high order numerics, you have to have a relatively large halo region. But for spectral elements or DG, you have communications just by the neighboring regions. This is from Ramnier's slide, and this is from the Giraldo's textbook. CG-DG have lots of properties, and they share many common features. They have very highly accurate interpolation and derivative because we can exploit the basis functions that are being used by them, and also we can also use the Gaussian quadrature formula to get highly accurate numerical quadratures. However, if we increase the order of the basis functions, the quadrature point tends to cluster near the element boundary. As you can see from this example here, the spacings here is very small. That tends to limit the time step very small. That's the one cost that you have to pay because there's no free lunch. You can use either nodal or modal basis functions. It's conservative, local operation. High order accurate. Actually, you can set the order of accuracy arbitrarily. If you want high order, you can just use a high order basis function, and it's done. Scalability is excellent, and also the grid is very flexible. You are not constrained by the grid orthogonality or the grids doesn't have to be equidistant, and still you can have a high order convergence. And it's very straightforward to have implement boundary conditions. The differences between CG and DG is that the CG, between elements, it has to be continuous. The function values has to be continuous, but for DG, element-wise, it can have discontinuity. So in order to enforce this, what we have to do a procedure just called DSS, that is direct stiffness summation procedure. If we do this, then that's how we ensure its C0 continuity. And generally for CG methods, stabilization strategy is required, either by by implementing hyperviscosity or some sort of modal filtering. For DG, the only communication that is being done is by flux calculation, and every numerical procedures are completely element-wise. And for this case, numerical flux method choice is very important. Now let me show you some results on the 1D, CG, and DG in shallow water results. Basically, what I wanted to do is when we learned about the high order properties of CG and DG, I wanted to see if it really does show the high order convergence. So a very simple example, we have a Gaussian hill with cyclic boundary conditions 1D. When we advect it, we want to see if it does show high order convergence. So this is a setup. And when we did the simulations with various combinations with varying basis function orders with CG, DG, you can have an exact numerical quadrature or inexact or exact. So with all these combinations combined, we do see what usually you expect for n order basis function, n plus 1 convergence rates. For this is n1, you would expect second order, n4, you would expect fifth order convergence, and then n8, ninth order, and n16, 17th order. But in real case, we see as here, the second and fifth order, we do see that the convergence rates are showing what we expect. But here, we don't see the convergence rate as we're expecting. For this case, we've used the Rinjakuda fourth order time integrator. And I thought that it's because of the time transmission errors are actually too big for this. So that's probably why we weren't seeing the actual theoretical convergence rates. So, and this is a problem. Well, it's never been a problem for finite volume because you never actually use high order numerics more than fourth order. So Rinjakuda fourth order was almost always enough. But for CG and DG, you can have arbitrary spatial order schemes. So now the time integration becomes a bottleneck. So I implemented Gottlieb 2005 M-stage M-1 order SSP explicit RK integrations. If you implement this, the nice thing is you have a general order time integration. So if you combine this with CG and DG, and if you match the orders together, then you have general arbitrary order schemes. So I tested the time integrator convergence from 1th order to 50th order, and it does show the theoretical convergence rates with very simple test case. Well, so the red line here is I just compared it for the well-known SSP formulas. And this is the RK fourth order classical one. So the time integrator is okay, but after I implemented this, I still wasn't able to get the high order convergence rate. The problem was the initial condition. In many cases, we use cosine with bell for initial conditions. The problem is the cosine bell on the second second derivative, we have a discontinuity if the other field is all 0. And because of this property, usually if we test high order numerics, we don't get high order convergence rates. So if you want to test high order convergence rates for advection, instead of using cosine bells, using Gaussian bell initial condition is advised. But I was using Gaussian bell, but the problem is at the edge, I'm using a cyclic boundary condition, and the first derivative at the endpoints, we see there's a difference here, and this is relatively big. So I had to decrease the width of the Gaussian bell so that the difference come within the machine precision. So if we apply all this and combine with high order time integrations, I was able to get theoretical convergence rates up to 17th order. And if we compare this with the classical RK4 time integrations, you do see that on the second order and fifth order, it does show the convergence rate, but with high order, you don't see the high order convergence rates. Also, you seem to meet some sort of a wall at here where this is the label here, it ends at 10th to 8th order, minus 8th order, but here it goes all the way to 10 to the 16th order, which is considered as a machine double precision truncation limit. And also, we tested this with various variable grid configurations. So this is variable in terms of element allocation. So the elements here is all regular, and then for the total domain, we for this we use it 2 times resolution, and for here we use an LGL type. So there's a clustering at the elements near the boundary, and the convergence rate seems to be very consistent. However, for LGL type, we did see that the L2 errors didn't perform well as the others. And we suspect this is because that there's a Gaussian hill over here in the middle, and the middle resolution is relatively coarse compared to others. So that's, I think, the initial condition representation is weaker compared to others, and that's why we're having a suboptimal solution compared to others. In terms of performance in wall clock, well, if you have a clustered grid, such like an LGL type I've shown before, that means there's a smaller element compared to the regular grid. So the computational cost increases exponentially. Right now for this, it's almost like 100-fold larger computational time is required in order to. So in regular cases, we would like to use the regular grid as much as possible. In terms of accuracy with respect to the wall clock analysis for regular grid, what we did find was that if we want to get a solution at some certain L2 error range, it does show that the high order, the 16th order scheme shows the best, the fastest solution gets there the most quickest. So, so the highest order schemes appears to be most efficient in terms of accuracy if you define efficiency like this. And the low order ones tend to be the most inefficient ones. This applies also to the shallow water, linearized shallow water cases. We do see this theoretical second order, third order, and so on. For 16th order, we're already reaching the machine truncation error regime, so we weren't seeing any error improvements at all. This is the actual numbers, the convergence rates. The second order we're expecting is 2.0 convergence. Third order with a 2.99, fifth order 4.999, and ninth order 8.99, and so on. So we are seeing theoretical convergence rates. For 2D global shallow water results, this is mostly done by Suction Choi. Where for the governing equations, we're following Geraldo 2001. The governing equation is written in terms of Cartesian coordinates, and so instead of having the continuity equation and 2 momentum terms, we're actually having 3 momentum equations combined with a Lagrange multiplier, so that the particle lives in the spherical shell. So let me show you some results with the animation. This is the cosine Bell result. And then it just go around, and so that's it. And then this is the deformational flow result. And this is the Rossby-Horowitz wave result. Oops. So the convergence rates for the cosine Bell, since it's a cosine, we're not seeing high order convergence rates as the ideal, the smooth rates. But the convergence rate is still high. Whereas the 6th to 8th order convergence rates we're seeing for CG, for DG similar to 5.72 to 7 point something. The DG results looks a little better than the CG. For the deformational flow, right now for these cases we're using 5th order time integrators, all fixed. So, but the convergence rates we're seeing is 6th order to 12th order, both for CG and DG. And this is the global steady state nonlinear zonal geostrophic flow for MP, the 4th order and 8th order. For For 8th order, we are already reaching machine truncation error regime, so we're not seeing any improvements. But for 4th order, we're consistently seeing like convergence rates of 5.6 or so, 5.7. And this is the difference between the final state and the initial state. One thing that's noteworthy is that we don't seem to see grid structure imprints in our results. We're not sure when we're compared to other literature results. This is quite unique, and we are investigating why we're not seeing any of the grid imprints. This is the Rossby-Horowitz wave from. This is the CG and DG results from day 0 to day 7 and day 15. So the conclusion is, well, first of all, is it practical to have high order numerics in the first place? Well, let's think about this. So in order to have high order convergence rates for idealized advection cases, it does indicate that high order schemes are more efficient. But for this to happen, you have to have a perfect initial condition. So the scheme tends to be very sensitive to the IC, and also the temporal distribution order must match the spatial order. So this is a big constraint. And in real world, like if we apply the scheme in the non-hydrostatic or hydrostatic models, then there are physics that foreseeings that terms that act like point sources that always cause problems. So in real cases, we expect we won't see very high convergence rates. But still, high order horizontal numeric having that is very good, and we do see lots of models that tend to use 4th order in the horizontal, like MCore or CAMSE or even IFS. And so maybe in the future, when we do find out that we need a higher order, then it's very easy to implement higher order by just increasing the order. And also, one thing that we can do is we can have HP refinement. This means H refinement is increasing the number of grids, which is the traditional, so increasing the resolution. P is increasing the basis function order. So if we increase P, we can actually decrease the element number to fix the total grid points. So we can still have the same number of grid points, but have high order numerics. So by doing that, we can alleviate the computation cost. And what we didn't do this, but we do hear from others that for high order basis functions, the scalability pattern becomes even better. So the summary is KIAPS is aiming to develop our next generation model within 9 years, and the development strategy will possibly be done in a unified CG and DG framework. And with CG, DG, we can have arbitrary order and spatial order, and with this time integrator, we can have an arbitrary temporal order. And I've shown you the high order convergence results for 1D advection and shallow water, and for global cases, no signs of cube sphere grid implementing. And DG does seem to be a little more, actually, 2 times or some so in terms of computational resource compared to CG. And we think this is due to the numerical flux computation. Results indicate that CG and DG are both very robust. Thank you.
Yeah, so I just want to point out that in atmospheric science, we never converge. It's not just physics. A lot of the reason that we might want to use something higher than second order accuracy relates to treatment of poorly resolved but not completely unresolved waves, like a wavelength 10 delta x or 6 delta x, where a 4th order scheme may perform far better than a second order scheme, not because we're anywhere near the asymptotic convergence, but simply because it happens, almost by coincidence, to treat these relatively poorly resolved waves better. So I just wonder if we're not getting a little carried away with the convergence here, because we're just never going to converge. It's more a matter of trying to treat the features that aren't that are poorly resolved a little bit better by using a slightly higher order.
I agree. And well, I'm not insisting that we have to use super high order, like 10, 20th degrees, but it is good to have the freedom of choice, and we can fiddle with HP refinement procedures, so we can actually increase the order of numerics while decreasing the number of elements. And see if that works better, then we can just use that. If it doesn't, then we can always use the low order ones. Yes?
Again, you give a thorough reasoning and list about why you choose that numerical scheme. But one thing you have not mentioned, which is important, is did you use A grid or C grid, and which result you get? So you didn't mention any about grid. That's what I'm curious.
Right now, all the computations, well, for the shallow water cases, we are showing inexact integration results, which means, well, spectral elements or DG, in our case, we used, it can be considered as an A grid result.
Okay.
But we can, if we want to, we can make it look like, behave like C grid. Yes.
So the CG or spectral element formulation has these nice mimetic properties that we heard about this morning in the contravariant formulation. I'm wondering if those are preserved when you do the Lagrange, the Cartesian with Lagrange constraint.
We did confirm, well, actually, the results came out very recently, so we haven't analyzed the results thoroughly, so we don't know about them. One thing what we do know is that mass is being conserved very well. Well, we'll have to look into that.
Okay, let me stop here. Thank you very much.